Hello, everyone. Well, I'm going to be talking today about something that I recently posted entitled, What is Ruliology? So the story is this. The concept of Ruliology really seems to be taking off. More and more people are talking about it. Question is, what is Ruliology? Well, since I invented the term, I had thought I should write something to explain what it meant. But then I realized I actually already wrote something back in 2021 when I first invented the term. And what I wrote back then was part of something a bit bigger. But what I wanted to do today was to go through the part that explains Ruliology. So I'll tell you what I had to say. So if one sets up a system to follow a particular set of simple rules, what will the system do? Or put another way, how do all those simple programs out there in the computational universe of possible programs behave? These are pure abstract questions of basic science. They're questions one's led to ask when one's operating in the computational paradigm that I talked about in New Kind of Science. But at some level, they're questions about the specific science of what abstract rules that we can describe as programs do. What is that science? It's not computer science, because that will be about programs we construct for particular purposes rather than ones that are just out there in the wilds of the computational universe. It's not, as such, mathematics, because it's all about seeing what rules do rather than finding frameworks in which things can be proved. And in the end, it's clear it's actually a new science that's rich and broad, and that I, at least, have had the pleasure of practicing now for about 45 years. What should this science be called? I've wondered about this for decades. I've filled so many pages with possible names. Could it be based on Greek or Latin words associated with rules? Well, there are arch and reg, very well-trafficked roots. What about words associated with computation? That would be logis or calc. None of these seem to work. But in something akin to the process of meta-modeling, something I've also talked about, we can ask, what is the essence of what we want to communicate in the word? It's all about studying rules and what their consequences are. So why not the simple and obvious Ruliology? Yes, it's a new and slightly unusual sounding word, but I think it does well at communicating what this science that I've enjoyed for so long is about. And I, for one, will be pleased to call myself a Ruliologist. What is Ruliology really about? It's a pure basic science and a very clean and precise one. It's about setting up abstract rules and then seeing what they do. There's no kind of wiggle room, no issue with reproducibility. You could run a rule and it does what it does, the same every time. What does the rule 73 cellular automaton starting from a single black cell do? What does some particular Turing machine do? What about some particular multi-way string substitution system? These are specific questions of Ruliology. At first, you might just do the computation and visualize the result. But maybe you notice some particular feature, and then you can use whatever methods it takes to get a specific Ruliological result and to establish, for example, that in Rule 73, in the Rule 73 pattern, black cells appear only in odd-length blocks. Ruliology tends to start with specific cases of specific rules, but then it generalizes, looking at broader ranges of cases for a particular rule or whole classes of rules, and it always has concrete things to do, visualizing behavior, measuring specific features, and so on. But Ruliology quickly comes face to face with computational irreducibility. What does some particular case of some particular rule eventually do? That may require an irreducible amount of computational effort to find out. And if one insists on knowing what amounts to a general, truly infinite time result, it may be formally undecidable. It's the same story with looking at different cases of a rule or different rules. Is there any case that does this, or any rule that does it? What's remarkable to me, even after all these years of Ruliology, is how many surprises there end up being. You have some particular kind of rule, and it looks as if it's only going to behave in some particular way. But no, eventually you find a case where it does something completely different and unexpected. And yes, this is in effect computational irreducibility reaching into what one's seeing. Sometimes I've thought of Ruliology as being at first a bit like natural history. You're exploring the world of simple programs, finding what strange creature exists in it, and capturing them for study. And yes, in actual biological natural history, the diversity of what one sees is presumably at its core exactly the same computational phenomenon we see in abstract Ruliology. It's actually something I've written about in recent times. So how does Ruliology relate to complexity? It's a core part, and in fact, the most fundamental part of studying the foundations of complexity. Ruliology is like studying complexity at its ultimate source, and about seeing just how complexity is generated from its simplest origins. Ruliology is what builds raw material and intuition for making models. It's what shows us what's possible in the computational universe and what we can use to model and understand the systems we study. In meta-modeling, we're going from models that have been constructed and drilling down to see what's underneath them. In Ruliology, in a sense, we're going the other way, building up from minimal foundations to see what can happen. In some ways, Ruliology is like natural science. It's taking the computational universe as an abstracted analog of nature and studying how things in it work. But in other ways, Ruliology is something more generative than natural science, because within the science itself, it's thinking not only about what is, but also about what can abstractly be generated. Ruliology, in some ways, starts as an experimental science, and in some ways is abstract and theoretical from the beginning. It's experimental because it's often concerned with just running simple programs and seeing what they do, and in general, computational irreducibility suggests you often can't do better. But it's abstract and theoretical in the sense that what's being run is not some actual thing in the natural world with all its details and approximations, but something completely precise, defined, and computational. Like natural science, Ruliology starts from observations, but then builds up to theories and principles. Long ago, I found a simple classification of cellular automata, starting from random initial conditions, somehow reminiscent of identifying solids, liquids, and gases, or different kingdoms of organisms. But beyond such classifications, there are also much broader principles, with the most important, I believe, being the principle of computational equivalence. The everyday course of doing Ruliology doesn't require engaging directly with the whole principle of computational equivalence. But throughout Ruliology, the principle is crucial in guiding intuition and having an idea of what to expect. And by the way, it's from Ruliology that we can get evidence, like the universality of Rule 110 and of the 2-3 Turing machine, for the broad validity of the principle. I've been doing Ruliology, though not by that name, for 45 years, and I've done a lot of it. Last 5 years it has been by that name. In fact, it's probably been my top methodology in everything I've done in science. It's what's led me to understand the origins of complexity, first in cellular automata. It's what led me to formulate the general ideas in new kind of science, and it's what gave me the intuition and impetus to launch Wolfram Physics Project. I find Ruliology deeply elegant and satisfying. There's something very aesthetic, at least to me, about the purity of just seeing what simple rules do. It doesn't hurt that they often make very pleasing images. It's also satisfying when one can go from so little and get so much, and do so automatically just by running something on a computer. And as well, I like the fundamental permanence of Ruliology. If one's dealing with the simplest rules of some type, they're going to be foundational, not only now, but forever. It's like simple mathematical constructs, like the icosahedron. There were icosahedral dice in ancient Egypt, but when we find them today, their shapes still seem completely modern, because the icosahedron is something fundamental and timeless, just like the Rule 30 pattern or countless other discoveries in Ruliology. In a sense, perhaps one of the biggest surprises is that Ruliology is such a comparatively new activity. But as I kind of catalogued in New Kind of Science, it has precursors going back hundreds and perhaps thousands of years. But without the whole paradigm of New Kind of Science, there wasn't a context to understand why Ruliology is so significant. So what constitutes a good piece of Ruliology? I think it's all about simplicity and minimality. The best Ruliology happens after meta-modeling is finished, and one's really dealing with the simplest, most minimal class of rules of some particular type. In my efforts to do Ruliology, for example, in A New Kind of Science, I like to be able to explain the rules I'm using just by an explicit diagram, if possible with no words needed. But then it's important to show what the rules do as explicitly as possible. Sometimes, as in cellular automata, there's a very obvious visual representation that can be used, but in other cases it's important to do the work to find some scheme for visualization that's as explicit as possible and that both shows the whole of what's going on and doesn't introduce distracting or arbitrary additional elements. It's amazing how often in doing Ruliology, I'll end up making an array of thumbnail images of how certain rules behave. And again, the explicitness of this is important. Yes, one often wants to do various kinds of filtering, say of rules, but in the end, I've found that one needs to just look at what happens, because that's the only way to successfully notice the unexpected and to get a sense of the irreducible complexity of what's out there in the computational universe of possible rules. When I see papers that report what amounts to Ruliology, I always like it when there are explicit pictures. I'm disappointed if all I see are formal definitions or plots with curves on them. It's an inevitable consequence of the computational irreducibility that in doing good Ruliology, one has to look at things more explicitly. One of the great things about Ruliology as a field of study is how easy it is to explore new territory. The computational universe contains an infinite number of possible rules, and even among ones that one might consider simple, there are inevitably astronomically many on any human scale. But okay, if one explores some particular Ruliological system, what of it? It's a bit like chemistry, where one explores properties of some particular molecule. Exploring some particular class of rules, you may be lucky enough to come upon some new phenomenon or understand some new general principle, but what you know you'll be able to do is systematically adding to the body of knowledge in Ruliology. Why is that important? For a start, Ruliology is what provides the raw material for making models, so you're in effect creating a template for some potential future model. In addition, when it comes to technology, an important approach that I've discussed and used quite extensively involves mining the computational universe for technologically useful programs. And good Ruliology is crucial is helping to make that feasible. It's a bit like creating technology in the physical universe. It was crucial, for example, that good physics and chemistry have been done on liquid crystals, because that's what allowed them to be identified and used in making displays. Beyond its pragmatic value for models and for technology, another thing Ruliology does is to provide empirical raw material for making broader theories about the computational universe. When I discovered the principle of computational equivalence, it was as a result of several years of detailed Ruliology on particular types of rules. And good Ruliology is what prepares and catalogs examples from which theoretical advances can be made. It's worth remembering that there's a certain tendency to want to nail down Ruliology using, for example, mathematics. And sometimes it's possible to derive a nice summary of Ruliological results using, say, some piece of discrete mathematics. But it's remarkable how quickly the mathematics tends to get out of hand, with even a very simple rule having behavior that can only be captured by large amounts of obscure mathematics. But of course, that's in a sense just computational irreducibility rearing its head and showing that mathematics is not the methodology to use and that instead something new is needed, which is precisely where Ruliology comes in. I've spent many years defining the character and subject matter of what I'm now calling Ruliology, but there's something else I've done too, which is to build a large tower of practical technology for actually doing Ruliology. It's taken, well, more than 40 years now to build up what's now the sort of full-scale computational language that is the Wolfram language. But all that time, I was using what we were building to do Ruliology. The Wolfram language is great and important for many things, but when it comes to Ruliology, it's simply a perfect fit. Of course, it's got lots of relevant built-in features like visualization, graph manipulation, and so on, as well as immediate support for systems like cellular automata, substitution systems, Turing machines, whatever. But what's even more important is that its fundamental symbolic structure gives it an explicit way to represent and run essentially any computational rule. In doing practical Ruliological explorations, and for example, searching the computational universe, it's also useful to have immediate support for things like parallel computation. But another crucial aspect of the Wolfram language for doing practical Ruliology is the concept of notebooks and computable documents. Notebooks let one organize both the process of research and the presentation of its results. I mean, I've been accumulating research notebooks about Ruliology for more than 35 years now, with textual notes, images of behavior, and code. And it's a great thing because the stability of the Wolfram language and its notebook format means I can immediately go back to something I did 35 years ago, run the code, and build on it. And when it comes to presenting results, I can do it as a computational essay created in a notebook in which the task of exposition is shared between text, pictures, and computational language code. In a traditional technical paper, based on the mathematical paradigm, the formal part of the presentation will normally use mathematical notation. But for Ruliology, as for other computational X fields, what one needs instead is computational notation, or rather computational language, which is exactly what the Wolfram language provides. In a good piece of Ruliology and Ruliology presentation, the notation should be simple, clear, and elegant. And because it's in computational language, it's not just something people read, it's also something that can immediately be executed or integrated somewhere else. What should the future of Ruliology be? It's a huge, wide open field in which there are many careers to be made and immense numbers of papers and theses and books that can be written that will build up a body of knowledge that advances not just the pure basic science of the computational universe, but also all the science and technology that flows from it. So that's what I had to say. There's now a whole Ruliology category in my writing site that has lots of recent examples of Ruliology in action. But that was just a short story of what Ruliology is and how to think about it. So I see we have a variety of questions here, comments perhaps. I can try and address these. Well, there's a rather technical question from Harry about an estimate for the computational size of an electron in our hypergraph models, Wolfram Physics Project models. How many rewrite events are involved in an electron-like excitation? I don't know. There is one parameter we need to know in making the universe computational. The one thing we need to know is what is the elementary unit of time, which is related to the elementary unit of distance, the elementary unit of energy, and also the size of an electron. All these things are related. I don't know what the elementary time is, the elementary length is. Maybe the elementary length is around 10 to the minus 100 meters, much smaller than the Planck scale, I'm not sure. I had an estimate I made about 6 years ago for the size of an electron, which said it might be, in some model, it might be as big as 10 to the 30th elementary elements, kind of atoms of space might be in an electron. I think that's actually an overestimate. My guess is this, that the core feature of an electron is a very small feature of the structure of the hypergraph, and that much of what is in an electron is its energy. Its energy is represented as actual activity in the hypergraph. So in a sense, the idea is that like what happens with a black hole, the mass of the black hole is proportional to its size. My guess is that in this case, for an electron, the energy is sort of proportional to its size, still incredibly tiny. I mean, the actual limits that exist today on the size of electrons are around, I think, 10 to the minus 20 meters. So we're talking about things unbelievably many orders of magnitude smaller than that at any reasonable energy that one can generate in the universe, so to speak. So my guess is that the picture of an electron is that there's some kind of essentially topological core, and then there's a kind of big coating that carries the energy of the electron, and that's what one's dealing with. I think there's probably a very close correspondence between things like electrons and how they exist as kind of stable structures in the structure of space, basically, in this hypergraph that represents space, and the way that things like black holes operate. I think basically particles are like tiny black holes, something that I actually first thought when I was a kid, and people told me that's a stupid idea. I don't think it's a stupid idea. We'll see. There's a question here from Sam. Is the Ruliad growing in time, or is it a static object? Boy, I'm just writing something right now about metaphysics, which tries to talk about that question. The Ruliad is the kind of ultimate limit of Ruliology, in a sense. It is the entangled limit of all possible computations, and it is the thing which I believe underlies both physics and mathematics. So the Ruliad, you can imagine constructing it once and for all. It's all possible programs running for an infinite time, entangled by their common states that they generate. But we can't generate that. sort of from an outside view, from kind of a God's eye view, it's like, yep, you can just make a Ruliad. Here it is. There's the Ruliad. It's not a Ruliad, it's the Ruliad. It's a unique object. We can't make such a thing because the only way we make it is to do the computations that are in it. And the rate at which those computations get done are the rate that the universe is doing them. So I think there are two views. The Ruliad, for us, what we care about is, as entities embedded in the Ruliad, how do we perceive the Ruliad? And the big result is that for entities like us, for observers like us, who are computationally bounded, who believe we're persistent in time, it is inevitable that our perception of the Ruliad has to correspond to certain laws of physics that we know. So for observers like us, we can say, well, we can either say the Ruliad already exists in some sense, and we get to explore it in our computationally bounded way at a certain rate. It's already out there, but we're just crawling through it at a very slow rate. Or we can say, we have a different point of view because the Ruliad is an abstract thing. We can say, we're sitting here and the Ruliad is abstractly, we're considering the fact that it's abstractly building up around us. And in the end, the passage of time is either for us, our exploration of the Ruliad, or the building of the Ruliad around us as an observer. I mean, if you're into quantum mechanics, the two sort of pictures of quantum mechanics, the Schrodinger picture and the Heisenberg picture, are very much like this. Kind of the Schrodinger picture is more like the Ruliad already exists and we're moving through it. The Heisenberg picture, more like the Ruliad is kind of being created as we go. Let's see. Gosh, from Sam, how many radically different types of mind can parse the same piece of Ruliad at the same time? If it's more than one intelligence, what happens when they disagree? What happens to causation if, say, 10 different minds are sampling the same piece of Ruliad and all deciding what to do next? Causation is in the eye of the beholder. There is our trajectory through the Ruliad involves following some time-like curve, which is saying we are observers embedded in the Ruliad, and the thing that is us follows some path. There are things, what is us? What are we? Every day, you're eating things. There's more stuff that's coming into you. It's going to get turned into protein. It's going to get turned into glucose that runs your brain, whatever else. Some of it, you're sloughing off pieces of skin and so on. What is us changes over time, even at that very macroscopic scale. In the Ruliad, there's this question of the what is us. We are progressing through time as individuals, where we have this thing that we think of as us that progresses through time. There could be many different us's that progress through time, so to speak. Imagine that we have sort of a mind-like thing that is, the bacteria that are living inside you, the colony of bacteria, doing all kinds of computations and so on. But, every day you excrete out a bunch of those bacteria. They're gone. They're no longer part of the you. They're a different sort of parallel, well, I don't think they last very long, but they, you can imagine them being sort of a different kind of parallel thing that's doing what it does. So I think the answer is that the individual observer has a certain trajectory through the Ruliad. And there can be many different individual trajectories with different through the Ruliad. So, for example, us humans, we're all a big flock of observers going through the Ruliad, more or less aligned, more or less together. There can be another kind of observer that is something completely different, possibly something we don't really even recognize as, we might recognize it as a piece of nature, but otherwise we don't really recognize it, that is having its view. I mean, my commonly quoted thing is, the weather has a mind of its own, and it can have a point of view about the Ruliad, but it is going through us, where aeroplanes are flying through the weather, and, we've got all of our brain activity going on inside us. And, maybe the weather is disrupting some of that brain activity in some way. We're disrupting the weather's thought process, so to speak. But these are just different views of the Ruliad that are sort of intermingled in that sense. So I think, and I think this notion of causation is really in the eye of the beholder. Causation is associated with the thread of individuality that is a particular observer. Now, this question of what is the density of kind of observer-like things, even observers like us within the Ruliad. Observers like us, potentially with utterly different kind of sensory apparatus, detecting different kind of features of things. The way we aggregate up the structure of space might be different from the way something else aggregates up the structure of space. I think there are some constraints from computational boundedness, but I think that's a thing that one can expect. Now, I think it's a very interesting question. Can one derive the density of observer-like things in the Ruliad? The fact that the Ruliad exists is inevitable. The fact that we as observers exist within the Ruliad, or that observers like us exist within the Ruliad, is probably also inevitable. It's a piece of science we have to derive. And for example, observers like us have the feature that we do self-reproduction. And that allows us to have many observers who are similar, which is important in kind of having a triangulated sort of objective reality for those observers. And so I think that kind of it's like, can one derive the fact that there are going to be self-replicating things in the Ruliad? My guess is yes, but we haven't done that yet. That's a piece of future science to be done. Now the question is, what's the density of sort of observer-like things in the Ruliad? We don't know. One can imagine deriving that as a matter of science. It's not so easy, because finding a pocket of computational reducibility is kind of one of those things that you might happen to find it, like you might happen to find a piece of mathematical analysis that you can do, but it is not obvious how you go search for it. You can go use an LLM or something to go search for pockets of reducibility. I suspect those things are too close to us to find ones that are very alien to us. But, a very interesting question would be, you're thinking about, search for extraterrestrial intelligence, let's say, and you use the Drake equation, which I've never really believed very much in, to say in the physical space, what's the density of extraterrestrial organization, civilizations and so on, a very hokey thing to calculate. But what one might imagine is saying, in the Ruliad, what's the density of observers who are like us in certain ways in the Ruliad? Now, that's physical space is just one slice of how you can parse the Ruliad. So what we're asking for is, with respect to the hypergraph that is the structure of space, for example, what we could notice very different features of that for observers like us as for another kind of observer that's sort of coexisting in the Ruliad. So I think it's a super interesting question what the density of these things is. How far apart are observer-like things in the Ruliad? How far apart are kind of minds in the Ruliad? We don't know the answer. It is something conceivably scientifically accessible, but we got to do a bunch more work on that to understand it. Let's see. Ilka asks, how does Ruliology address the interaction of a system with its environment, the ecology of multiple systems interacting with each other and evolving in real time while obeying physical constraints? Does Ruliology address the question of information exchange between systems and learning? Ruliology is it's a basic science. It is talking about simple programs and what they do. And the best Ruliology has self-contained systems. It's talking about what the thing does when it's not being kicked by something from the outside. If you have a system where every single moment what it does is determined by what's happening on the outside, you might as well not even talk about it as a system for itself. A system tends to be something where it has some inner life that's doing something. Every so often it might get kicked by the outside, but mostly it's just doing what it does. And that's what Ruliology really specializes in, the intrinsic dynamics of systems. Now, you can ask, how does a system with certain intrinsic dynamics respond to noise, perturbations from the environment? I've done quite a lot of work on that recently, particularly applying that to foundations of medicine, thinking about kind of what effect that has. We've thought a lot in the last couple of years about foundations of biology. In that case, you are kind of saying there's the intrinsic development of an organism, and there's a dice being rolled to determine how the rules might get mutated, and that's the thing one can look at. The question of the ecology of multiple systems and their interaction, that's an interesting one. Actually, as it happens, I was literally just looking at something that I started looking at 40 years ago or something now, which is kind of games between programs. You have, let's say you have multiple, you have something where you're playing some game in an iterative way. And what's playing the game? What's playing the game is little tiny programs. And you say, well, which programs win? You have a tournament among programs, which wins? I think there's some really interesting stuff to figure out there, where the core methodology is really Ruliology. You're enumerating possible programs. You're not saying, let me kind of think a bit and invent a program that's going to be studied for this. You're just searching the computational universe for all possible programs. When it comes to learning, neural nets, for example, are very big, complicated programs. I've been interested a year and a bit ago, I was interested in kind of how can you understand the essence of what's happening in neural nets at a very foundational Ruliological level. And I found out that even some very, very simple programs are capable of having the essence of what happens in machine learning, and you learn a whole bunch from doing that. One of the things I was doing there was trying to make neural nets Ruliological. A typical neural net, it's very complicated, it's very hard to visualize. If you say what's qualitatively going on in this neural net, you can look at all kinds of random things. It's very hard to tell what's qualitatively going on. I tried to boil it down to the point where you could say, here's a picture of what's happening and you can understand the picture. It's not a bunch of connections which are just randomly connecting this to that and so on. And a lot of progress. There's a lot more to do there, but that's a really interesting thing, is to make machine learning, for example, Ruliological, because you learn a bunch from it. There are, I'm sure, some core laws of machine learning to be learned. I mean, just to say, one of the big things that's emerged from our physics project is that what is ultimately down there in the Ruliad, in the sort of set of all possible Ruliological processes, what is down there, when observed by an observer like us, you extract certain aggregate laws, like general relativity, like quantum mechanics, like the second law of thermodynamics. The same thing happens in metamathematics. You extract certain big laws of mathematics, the most important of which is that you can do mathematics at a high level you can talk about the Pythagorean theorem without always having to footnote the definition of real numbers. So there's an interesting question. In biology, for example, there are similarly big theories, like the fact that biological evolution is possible, or the thing I've recently worked on about Rulial ensembles as a way to understand the effect of kind of fitness for the organism on the microscopic structure of sort of the bulk orchestration of its molecular processes. In machine learning, my guess is there are global laws of machine learning that one can learn that are kind of like the global laws of fluid mechanics relative to molecular dynamics. We're still doing molecular dynamics always in machine learning. We don't know what those global laws are. Those global laws may talk about things that are very interesting to us and very relevant technologically, or they may talk about things that are just like, well, that's amusing, but it doesn't really matter for what we have to do technologically. I don't know yet. Jesse is asking, how complicated is the rule that describes our universe? That's actually a complicated story, because in the Ruliad, what one is saying that all possible rules are running in the universe, and we are just observing a slice. The rules that we may attribute to be the rules that are running the universe, it depends on us as observers, what rules we attribute to running the universe. And what happens a little bit like what happens in fluid mechanics. You still get the same laws of fluid mechanics, even if your molecules underneath are different shapes. It doesn't matter. There are certain parameters where it matters, and those, I think, what those parameters, the general conclusions of the laws of physics don't depend in micro detail on what the rules are. Certain other features, like the particular mass of the electron and so on, undoubtedly do depend on that. And they undoubtedly, but what's happening is more that we happen to live in a certain part of the Ruliad, and so that's the physics we observe. I mean, take something like the mass of the electron. You might look up the mass of the electron, 0.511 MeV, but that mass is a mass for observers who don't transfer much momentum to the electron they're looking at. the mass of the electron changes if you're a different kind of observer. That's a well-known fact in quantum field theory and particle physics. It's been known for 50 years or something. But that's just one sign of the fact that sort of all of the universe is observer dependent in some sense. So that's it's actually something I should mention in the things I'm writing about metaphysics, I realize. Anyway, Kathy asks, is Ruliology closer to mathematics, computer science, or physics? I don't know, which is closer, physics, mathematics, computer science? Those form points in the space of things you can study. Ruliology is another point. I think, I don't know if I'm to say which is it closest to, it's kind of equidistant between mathematics, computer science, and physics. It's occasionally, it informs mathematics. It's like experimental mathematics. It tells one, it puts up things that are mathematically interesting. Occasionally, mathematics can say things that are interesting for it. Exactly the same story for computer science, and kind of the same story for physics. I would say the methodology of doing experiments is a little bit more developed in physics than it is in these other fields, but yet the idea of exploring wide classes of models is not as developed in physics. Physics, it's like we're doing this particular model and seeing its consequences. I mean, I would say you can also ask how close is Ruliology to something like chemistry, where you're looking at molecules and seeing what they do. It's another thing that is methodologically somewhat close. Right now, well, we don't yet know the full links between Ruliology and chemistry. My guess is those links will emerge. That's sort of a different direction. Gary is asking, does Ruliology change what we mean by understanding a system if computational irreducibility limits prediction? In a sense, it does, yes. I mean, we can say, can we simulate the system? That's something we can do even when there's computational irreducibility. Can we wrap our arms around the whole thing? It's saying, no, you can't do that in many cases. Now, the truth is, mathematics is very much a wrap one's arms around the whole thing kind of field, where it's like, let's prove a theorem. Let's say what's generally true about something. Physics, let's have a theory. Computer science, less so. Computer science, it's like, well, we've got this system and it can do all these kinds of things. It's not like we wrap our arms around everything that system can do. It's more like we have a thing and it does lots of stuff. And that's a little bit more like the kind of open-ended story of Ruliology, I think. Gary also asks, is computational irreducibility a limitation or a central feature of Ruliology? Computational irreducibility is a fundamental fact of Ruliology, just like Newton's laws or something are a fundamental fact of physics. They are one of the conservation of energy is a fundamental fact of physics. Computational irreducibility is something that is a fundamental thing that informs Ruliology and that Ruliology can study. Just like, let's say, the laws of mechanics in physics, given the laws of mechanics, many things follow. Given computational irreducibility, many things follow, and you can study it. William says, I like the term Ruliology, good. For a compilation of abstract paintings I did on the subject. Okay, it'd be interesting to see. Called it the solution space. Ruliology is more poetic. Good. For the next collection of paintings. Nightmare asks, will you do more live streams about the Ruliad? I should. Actually, one thing I should do at some point is just a live stream going over what I wrote about the concept of the Ruliad a few years ago. I think that would be a useful thing to do. At that time, I wasn't going over things I'd written in this way, and I'd like to do that. Let's see. Ty is commenting, they're reading about a guy called Harry Wiener, who invented a thing called the Wiener index in chemistry. And it's, yeah, you can, I think, if you use molecules in Wolfram language, you can compute Wiener indices for molecules. They're basically, you take the graph of how the bonds in the molecule are connected, and it gives you a characterization of kind of that, the bond connections of a molecule, and it's related. You can do things like try and work out the boiling point of that that compound based on that. It's part of the usually called quantitative structure QSAR, quantitative structure, oh my gosh. Quantitative structure properties relationships. Anyway, commenting that this is, so that's an interesting thought. I mean, to have something like a Wiener index for, by the way, it's not the same Wiener as the Norbert Wiener, it's a Harry Wiener. But no relation as far as I know. Norbert Wiener was a person involved in cybernetics and sort of in the pre history of Ruliology. The question is, what can you say? Okay, so if I give you a molecule and say, what are the properties of this molecule? In general, that's very hard to answer. I mean, if you say, what's the reaction rate of this molecule with that molecule? That's super difficult to work out that quantum chemistry to do that. It's beyond the state of the art to do that for anything beyond the tiniest molecules. So the question is, you just show me a molecule, what can you say about its properties? Generally, not a lot. Show me a rule, what can I say about its properties? Show me some simple underlying rule. There are typically a few things you can say. Will the rule produce patterns that increase without bound? Sometimes you can easily answer that. My guess is, and it's a reasonable question, an interesting question, to what extent are there things you can identify that's like, given these rules, there are this and this and this things you can compute directly from the rule very easily, and that tells you something about how the system will behave. And I think the answer is probably yes. But beyond that, in Ruliology and in chemistry, you're stuck with computational irreducibility. That is, given the rule, it's very hard to tell what the consequences of that rule will be. Given the molecule, it's very hard to tell what all the properties of that molecule will be. The Wiener index is an example of biting off a particular simple property of the molecule and being able to do certain things like boiling points from that in that particular case. And yes, that's a reasonable thing. I mean, I don't know necessarily what the analog of boiling point is. Maybe it's expand without bound. An interesting question. Yeah, it's a good project actually. Look at some of those things. Katie asks, is the computational universe bigger than the physical universe? Absolutely. The Ruliad is bigger than the universe. The physical universe that we perceive is but a slice of the Ruliad. It is the slice of the Ruliad that's around where we are in the Ruliad. There's a lot else in the Ruliad, exponentially, infinitely more in the Ruliad than the part that we perceive. It's a little bit like in physical space. We're sitting on this planet and we know all kinds of things about this planet, but somebody says, hey, wait a minute, there's all those other exoplanets out there and planets in other galaxies and so on. There's just a lot else out there. And that's the situation we're in our physical universe relative to the computational universe and relative to the Ruliad. Now, one thing that's interesting is that in physical space, when we are trying to go from here to there, we have to get a rocket and try and go there, and we haven't managed to go very far yet. In the Ruliad, you actually can just write down a rule and just say, make it so, go there. Just start simulating that rule. It's kind of a different situation. It's kind of interesting. Now, you can't necessarily transport your way of thinking about the world to what happens with that rule. It's an alien thing you get to, but you can kind of, you can jump there. It's a bit different from what happens in physical space. Let's see. Dream is commenting, the cool thing about the Ruliad, other than understanding us, is going deeper and getting to understand other types of entities, materials, complexities that might be created in other planets or in things that aren't planets at all, but are just sort of features of Ruliology, features of the Ruliad. Yes. I mean, I've tried to understand a bit about kind of the how alien minds, I've been very interested in this question of alien minds and how alien minds would think about things, because I'm just stuck with the mind that I have. And I try to expand my mind and think in different kinds of paradigms, but I'm pretty much stuck with the 100 billion neurons that currently, reside in this brain case type thing. But can one imagine what it would be like to be an alien mind? I've tried to do that a bit. You can take an AI, for example. Something I've done is you take a generative AI that's generating images, and you say, a standard thing, you say, make a picture of a cat in a party hat, and then you change its mind. You change the structure of its mind to make it alien and say, well, what do you now think a cat in a party hat looks like? And the answer is you get all this weird stuff. And that's kind of a picture of the mental image of an alien mind. And so that's one effort that I've gone to sort of get into what it's like to be in an alien mind. Let's see. I'm realizing many things that I need to mention in this piece that I'm writing about metaphysics, like the concept of interconcept space and things about individuals and so on, things I've been talking about here. Thank you for prompting me on these things. So Leon asks, would a dog, an elephant, or a bat live in the same subset of types of observers like us? To some extent, yes. To some extent, no. The very basic features of observers like us, that we are computationally bounded, that we believe we're persistent in time, that we have a single thread of experience, dogs, bats, elephants, they all have the same point of view. That's why we can have any hope of sort of communicating, understanding those kinds of critters. Now, the detailed sensory data that they get is different. Dogs, smell is a big thing. Elephants, infrasound is a thing. Bats, ultrasound is a thing. The kinds of physics that a dog might want to discuss are probably different from what we would want to discuss. For us, we say, I see that thing. It's an object. It's I move these objects around. I can do the laws of mechanics. Here'd be a good example for a dog. For us, the laws of mechanics are important. Force equals mass times acceleration. You've got an object, a solid object, you're moving it around. If you're a dog, you might care a lot more about the scent of things, but scent is a gaseous thing, and the laws of motion don't apply to it. The same laws of motion that say you exert a force and then it moves, well, they apply microscopically to the molecules, but there are no doubt other laws of motion that are relevant if you're smelling things. In other words, if you there'll be air currents that move around, and there'll be patterns to those air currents, and there's a whole physics to those things that we might know from fluid mechanics, but there may be aspects of that physics that are really important if you're a dog going sniff, 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 and pulling little packets of scent and so on, that are just like, for us, it's like, oh, we didn't think of that. That's not something that our science ever studied. So you can imagine the same kind of thing with infrasound, for example. Infrasound, low frequency sound, very long wavelength, it'll diffract around things. I have no idea what the world looks like in infrasound. I mean, it's even, you can get a little thing that, clips onto your iPhone and shows you the world in infrared. And the world's a weird place in infrared. I mean, things that you thought, it's like you look at a person who's wearing glasses in the infrared and their eyes are really cold relative, the surface of their glasses is not heated by their internal thermoregulation. And, as an example, but there are a lot of things where you look at the world in infrared and it looks very different. And you can imagine that the kinds of things you would want to have, the kinds of laws about the world you might want to have, would be different if you lived in the infrared, so to speak, if that was your sensory data. You can go much further away than those kinds of things that don't anymore have the notion of a single thread of time. For example, if you're a plant, I doubt you have a notion of a single thread of time. In other words, animals, because they move around and so on, they kind of like, I have to go to this place now. If you're this thing that's spread out, some big lump of lichen or something that's spread out over a big region, and something happens in one part, and then something happens in another part, the notion that you have a single thread of what's going on, I don't think really exists. And so that's a place where your view of the universe will be different because you don't have this idea of a single thread of time. And for a lichen, certain kinds of pieces of mechanics, it'll be different what you care about. Let's see, Technic is asking, Okay, technique is asking, if all possible rules are running in the universe, couldn't there be a rule that goes from the empty set directly to the universe as we see it at the moment? Doesn't this lead us to a Boltzmann-brain sort of conundrum? The answer is yes, you can have such a rule, but observers like us who are computationally bounded will not be able to tell what was going on in that rule. So in other words, as we pick through the Ruliad, we are picking through it in a computationally bounded way. So if somebody says, look, here's this giant thing that just happened, we'll be like, that's really confusing. We can't tell what happened. I think that's the answer to that conundrum. So in other words, the kind of, as we parse through things, we're only capable of kind of understanding it in terms of quite small rules. It's an interesting question from Jani. Has your aesthetic sense, what you find beautiful in rules, changed over the years? That's a very interesting question. I mean, I think it changed for funny reasons early on, because very early on, I was displaying things by printing out a bunch of stars and spaces on line printers. Then I started using bitmap displays, but they were fairly low resolution and they were black and white. Then by, color displays were kind of luxury in the mid 1980s when I was early times working on this. And then later on, uh, I would say I didn't really go sort of full color for everything until probably the end of the 1990s of really routinely sort of seeing things in color, as opposed to, oh, I don't know, the next computer was black and white, and my book, New Kind of Science, everything was in black and white. So a little bit of change associated with those kinds of things. I would say the other sort of aesthetic change is what can you visualize? I mean, in other words, okay, so a cellular automaton is a great thing to visualize. It's just a grid of cells. You can make a picture of it. People often try and make movies of these things, and I find that much less interesting than a picture of the sort of space-time history of the thing. Something that I started doing in the 1990s and really accelerated in recent times with our physics project is visualizing things which are based on graphs. And that really became possible in a serious way in the 2010s when we introduced kind of graph visualization in Wolfram language. And I would say my aesthetic of making graphs is a little different from my aesthetic of making arrays of bits, of pixels. I think the 3D case, still haven't really internalized the 3D case. Most 3D objects that I make sort of ruliologically, I can see their exterior boundary. It's kind of like I can see the bones in the X-ray. But if you ask me what is volumetrically happening, it's like flying through a cloud. You can't really tell what's going on. It's just all white there, even though there's different pieces of white. Inside a cloud, there's all kinds of internal structure, just as you can imagine from looking at the fluffiness of the outside of like a cumulus cloud. But if you're flying through it, it's just all white there. So, I don't think I have a good way of visualizing the fog, so to speak. And I've tried over the years, I even tried back in the beginning of the 1990s, beginning to use kind of virtual reality as a way to visualize these things. It was pretty crummy at that time. I used it maybe 5 years ago and discovered that I get horribly motion sick, and at least at that time. Haven't really tried it in the very latest iteration of virtual reality. My team got a little bit burnt out from having been done virtual reality a few times before. It's like, when's it really going to take off? But I think I might get a different aesthetic sense by being able to be in virtual reality inside sort of 3D objects and so on. I don't know. But in terms of kind of what's a nice cellular automaton, I think it's been fairly constant over the years. It's kind of like these very organic forms. I think probably a few things changed because the resolution of displays got bigger, and I could start seeing vastly bigger things where what had been kind of, oh, that's pretty interesting, that pretty interesting thing on a higher resolution, bigger display, that was just mushed in some tiny corner. And what was really interesting was the much bigger structure on a scale of 1,000 pixels, as opposed to a little structure on a scale of 5 pixels. But interesting question. Let's see. James asks, can you make parallels between Ruliology and blockchain, i.e. rule-based systems, or could you explore a set of possible rules of a programmable blockchain and Ruliology? I've studied this a bit, looking at different possible simple rules for example, achieving the consensus that you need in blockchain. You know, different people are sending in transactions. It's like you got to decide what is the next block on the blockchain? What is the consensus result for how that works? There's a question of sort of how do you aggregate consensus? And in fact, people have used a bunch of things I did in New Kind of Science and Ruliology to make consensus algorithms. There are several blockchains that essentially use Ruliological consensus algorithms that were found by searching spaces of simple programs, or maybe I'd done the searches and they used what I found, but to do that. So yes, Ruliology is very relevant to things like that as a way of kind of finding a solution for the problem of distributed consensus. I think that the question of sort of what does an autonomous blockchain do? I mean, blockchains as they exist today are mostly humans are doing stuff. Humans are doing transactions. There are some smart contracts that are automatically executing, but you know, one could imagine that at some time in the future, when that most of the activity is autonomous activity. Most of what's going on blockchains is you set up a program, and then the blockchains go at it, and all their contracts fire, and there's huge, you know, dominoes of effects of whole rafts of 10,000 contracts that executed one after another as a function of something happening. And you essentially have sort of blockchain civilization at that point, where things are happening autonomously in the blockchain without human intervention. And every so often something intersects with some human thing. I mean, it reminds me a few years ago, we were studying sort of the use of physics project ideas on the blockchain and sort of quantum ideas that come from our physics project for blockchain. We never really finished that. It's now sort of recursed into a study that I've been doing about the foundations of economics. Hopefully that will see the light of day at some point. But the joke we always were making at that time was, you know, all kinds of things happen really logically down there in the details of programs running. But in the end, the transaction results in somebody driving the car off the dealer's lot type thing. In other words, something eventually happens in our real world from it. And that's kind of a, you know, but there's a lot of stuff that can happen down at the level of automated contracts firing and things like this. Mark asks, can you compute a similarity distance between rules? Can they be placed on a manifold? Very interesting question. The rules themselves, that's not very interesting. I mean, it's just a, you know, Cantor set topology or something like that for most kinds of rules. The underlying rule is just a bit sequence. And it's like, you know, any way of, you can put bit sequences on corners of a Boolean hypercube or whatever else. That's not very interesting. The thing that's interesting is the results, the morphology, the patterns that are generated from the rules, how do they relate to each other? Can you have a sort of a space of those rules? What is that like? Well, that's a big piece of the story of the Ruliad, is what that space is like. And we know a certain amount about it. In fact, a big thing we're studying right now is what I call infrageometry, which is kind of a generalization. Okay, so infrageometry at first is a generalization of geometry that works for things like hypergraphs instead of simple Euclidean space. In other words, for ordinary space, you look in an infinite microscope, you'll just see a little manifold that is just a piece of Euclidean space, a piece of ordinary space with coordinates and all that kind of thing. Even if the whole space might be curved and have all kinds of features, microscopically, it's just like Euclidean space. For what we want with our hypergraph systems and so on, microscopically, it's a hypergraph. It's not Euclidean space. So we're trying to build what we call infrageometry that tries to address kind of how the what geometry is like when it's not based on thinking about little patches of Euclidean space. So we've got what we call infrageometry that's based on hypergraphs. We've got sort of another level of infrageometry that we can call multi-way infrageometry that has to do with multi-way systems where it isn't a single rewriting of the hypergraph, but there are many possible paths. We have what we're calling causal infrageometry. And then the final big picture would be Rulial infrageometry, of infrageometry on the Ruliad. We've still got a ways to go on these other kinds of infergeometry, but that's the place we really can start talking about what's the geometry on the Ruliad. Now, I will say something that's a very fancy piece of mathematics. The Ruliad, this entangled limit of all possible computations, it's a very natural kind of object. And although people hadn't really studied it from a computational point of view before, even really thought of it, in mathematics, in category theory, which is a way of sort of idealizing the structure of certain kinds of mathematics, there is this notion of kind of higher category theory. Category theory is about kind of, you have these kinds of objects and you have transformations, morphisms between those objects. You build up these categories, you build up sort of categories, morphisms between categories and things. You build up higher categories. You keep going, you keep going. You build up higher categories. So it's like if you're doing mathematics, you can say in ordinary mathematics, you make a proof. You go from this thing to that thing to that thing. That's like a series of morphisms in a category. But then when you say, well, let's make transformations between proofs, that's a sort of higher category kind of question. You make transformations between there are two different proofs of this thing. How do they map onto each other? Then you say, well, I've got these sets of proofs that are mapped onto each other. How do I map between these mappings between sets of proofs? You keep going to an infinite level. You get to a thing called the infinity groupoid, which was introduced by a very pure mathematician named Alexander Grothendieck sometime, I guess, in the 70s, 1970s. And the infinity groupoid is a mathematically similar object that comes out of higher category theory and other mathematical theories. It's a very similar object to the Ruliad. And Grothendieck had a conjecture that he said, in this infinity groupoid, there will inevitably be topology and maybe geometry. It's sort of a frontier thing in areas of mathematics to imagine how will you inevitably get geometry from a thing like the infinity groupoid. And that's a very similar question to how will you get inevitable geometry from the Ruliad. We're working on it. Very interesting problem. It's pretty heavy lifting. It's kind of, it's heavy lifting on a scale where we're trying to do something where if you think about mathematics that's been done, the few million theorems of mathematics that have been produced, they're kind of going a certain distance. We're trying to jump at least approximately a really long way relative to those millions of theorems to be able to make these general statements. It's like a very big program of mathematics to get there, but we're working on it. Okay, there's a question here from Sotiris. Is the hyperuliad something beyond the Ruliad as constructed once you assume the Ruliad? In a manner similar to the fact that you can construct the rules once you assume the rational numbers. Yes, this is a complicated can of worms. The Ruliad is the entangled limit of all computational processes. What is a computational process? It's something you get by running a Turing machine, any other universal computer. Well, there are things that you can't get by running a universal computer for any finite amount of time. There are computations where it will necessarily take the universal computer an infinite time to do it. But you can imagine just saying, well, let's just assume we've got a magic box that has the answers to those infinite time computations. Let's make a new computer that has the magic box connected to it. Now we have a hypercomputer that is capable of doing things that ordinary computers can't do. Let's make a hyperuliad that comes out from all of the features of those hypercomputations. The same thing, the entangled limit of all possible hypercomputations. And by the way, there's not just one level of hypercomputation, there's an infinite number of levels of hypercomputation. There's a whole hierarchical lattice of hypercomputational levels. And each one of those defines a hyperuliad. Now, the question is, well, why does that mean is the Ruliad unique? Well, we right now think of ourselves as observers doing computational kinds of things. So we're kind of sitting in the Ruliad. To an observer in the hyperuliad, how different does the hyperuliad look to an observer like us in the ordinary Ruliad? If we are to be observers in the hyperuliad, we have to be doing hypercomputation ourselves. My guess, unproven, is that there is a kind of Rulial relativity, that to a hyperobserver in the hyperuliad, everything looks the same as the Ruliad looks to an observer in the Ruliad. Now, and it's fairly easy to see that there can never be communication between different Ruliads, between the Ruliad and hyperuliads, or between different hyperuliads. Once you're an observer in hyperuliad, 7, 2, 5, 6 specified by this path in the arithmetic hierarchy and so on, then that's where you are, and you'll never be anything else. And no dynamics of what happens in the Ruliad, in that hyperuliad, will ever kick you out of the hyperuliad, just as no dynamics of what happens in our Ruliad can get you to the hyperuliad. So, I mean, there are a lot of interesting questions about kind of hyporuliads, things simpler than the Ruliad, kind of computations that are simpler than the general computations in the Ruliad. What does a hyporuliad look like? It looks like a black hole. A black hole is a place where time stops, where you don't get to do an infinite thing. You don't get to do an unbounded thing. So I think a hyporuliad is kind of a black hole within the Ruliad, within a thing that would be described as the Ruliad. And we say, well, okay, what's happening in the hyperuliad? Well, we can't know because there's an event horizon that prevents any information coming out from the hyperuliad. That's how I think it works. Let's see. Weasel says, I've always wanted to know what plants think or how they feel. Do they make sound? I'm sure living life inside them that has something in there. I mean, some plants move, right? And so we can we can sort of tell what they're thinking at that level. We can sense chemical features of plants, just like, we can sense chemical features of ants or even humans. And, what does that mean they're feeling? We can sense chemical features of skunks and we can tell things from that. I don't know how we could tell, what it's like to be a plant. I have a feeling one of the very confusing things is there isn't a single thread of experience. And I think a lot of our experience of the world and our way of thinking is based on the fact that we have this single thread of experience. If you start having two threads of experience going in your brain, it's you're sort of nuts relative to the world at large. Maybe it all makes sense to you inside, but to anybody else interacting with you, it's like, what the heck is going on? This brain doesn't make sense. So I think that's sort of an extreme version of that, probably in our experience of kind of the thinking, the life, the mind of a plant type thing. All right, well, a bunch of very interesting questions, and you're giving me prompts for the things I'm trying to write right now about metaphysics. So thanks for joining me, and I see some requests for me to talk about the Ruliad another time, and I'm happy to do that, and see you another time for that. Thanks. Bye for now.